All right, this is a solutions video where I'm walking through the problems from assignment recently from our unit. And it's specifically related to problems in objects in equilibrium, rotational equilibrium. Number one, a uniform ladder of mass M and length L rest against a smooth wall, so no friction over here, at some angle theta naught, as shown in the figure. What is the torque due to the weight of the ladder about its base? So the term about its base means that the axis of rotation is at the base. That's what that means, about its base. And they want to know the torque due to the weight. And the weight is equal to the force of gravity, magnitude of the force of gravity acting on the ladder. So that's the torque that we need to know. So the definition of torque is given here, which is the moment arm times the force, which is equal to the R, which is the distance from the axis of rotation to the location where the force vector is, times the sine of the angle. So if I look at that and try to use this equation that we typically use in class, R F sine theta, I get the value of R, which we know as L over 2, because it's half the distance, times the force of gravity, which is mg, times sine of alpha. But none of my answers have alpha in it. And so, like, what do we do now? Well, if you draw this triangle over here, we know that this is L over 2. We know this is this angle that's in the problem. And this is the location at which the force of gravity is, which is downward. There's force of gravity. And notice this is a right angle. And this is that R, the distance R that's perpendicular to the force that we're interested in. And so I need to find R, this moment arm, in terms of things that are in the answer. And so that's when we know that cosine of that angle is equal to the adjacent divided by the hypotenuse, which is L over 2. And then I can solve for that, and I can use that part of the equation. And you will find the torque caused by the weight is equal to L over 2 times cosine of that angle times the force of gravity, and that is the answer D. So that was tricky because you actually had to use the distance R that was perpendicular to the force vector. Don't see too many of those. Okay, so here is an object, a rod. I see lots of these on the exams. I have lots of different forces. You got to pay attention to the arrows so you know which direction they go. Go and put your torque direction. So F1 and F2 will cause it to go counterclockwise. So those are positive torques. I actually went ahead and calculated them. And then F3 and 4 will create negative torques, and I calculated those. Now, 2 of the 4 forces will be put on this object at one particular time. So if I have force 1 and 2 that are exerted on the stick will have the greatest change in angular momentum. Well, the greatest change in angular momentum, torque times some period of time equals the change in angular momentum. So which one has the greatest torque? Well, when you put both of F1 and F2, your net torque is equal to 200. Notice that both F1 and F2 are in the same direction. So the only other option would be F4 and F3 added at the same time. And if you add those two torques together, it would be negative 125. So A is true. And so that is our answer. However, you can go and prove that B, C, and D are not true. F1 and 3 are exerted. The stick will not change its angular velocity. In other words, the net torque would be 0. And there is a net torque of something other than 0, so B is incorrect. C, F2 and 3 are exerted. The change in angular velocity per unit time will be in the clockwise direction. I find it to be positive, which means it's counterclockwise. F3 and 4 will have the smallest change in angular velocity per unit time, but notice 3 and 4 are in the same direction. If I wanted to create the smallest amount of torque, I might want to pick 2 that are in opposite directions. And sure enough, if you picked either F3 and F1 or F3 and F2, you'd get a smaller net torque. So again, C can't be true, D can't be true. So A is true. All right. I got another situation where I have this beam. I have a hinge. This is a hinge, and we haven't talked about this in class, have not talked about it. At a hinge, I actually have a force upward from the hinge and a force outward from the hinge. And it's not going to matter on this problem because I can select that as my axis of rotation, because what they want to know is the magnitude of the torque that the cable exerts on the beam. So its net torque is 0. There's 2 torques. I have the force of gravity acting on it. And so this is the torque 1 minus torque 2, which is the torque that's being applied by the cable, and that's what they want to know. They just want to know the magnitude of the torque. So all I have to do is solve for torque 2, and I find it to be equal to mgL naught over 2. So again, the net torque has to be equal to 0. I selected that pivot point P as my axis of rotation because I don't know anything about that area, so I get rid of all those torques, and I find that 0 equals the torque created by the weight, which I called T1, minus the torque 2, which is the cable's torque, and I just solve for T2 and plug in the values for T1. All right, so we got a situation where I have a meter stick, and it's got a pivot point right here, and I have some objects, and they hang, and then they give me some more data. So they tell me exactly how much they weigh, the masses of each object and their location, so I know all the things related to their torques. So I know that this one's going to be positive because it's counterclockwise. The magnitude of that torque is positive 2.5 Newton meters. This is going to be negative. The magnitude of that is negative 5. The net torque between those two would be 2.5 minus 5. I get negative 2.5 net torque. So it's going to accelerate. It's negative. Oh, negative is clockwise. Yes. Okay. Now let's go look at all the things. The system will rotate clockwise with a constant angular speed. If I have a net torque, which I do, alpha or angular acceleration is not equal to 0. It can't have a constant speed. So A is wrong. The system will rotate clockwise direction with an increasing angular speed. Yes, the net torque is something other than 0. It will increase in angular speed. C says counterclockwise, which is positive, and we found it to be negative. So C and D are incorrect. Same situation, same picture, but maybe some different values. I calculated all the torques, and then I look and see which one is correct. Notice the net torque I found in this problem to be 0. Net torque exerted by force of gravity creates the greatest torque on the meter stick. Well, where's force of gravity? Right here. This is an axis of rotation. Force of gravity is right through it. So force of gravity creates 0 torque at about that pivot point. This can't be true. The torque exerted by 1 is the greatest torque. No, they actually have the equal torque because they cancel. The torque exerted by 0.5 is the greatest torque. No, it's D. The torque are equal to one another because we found it to be the same, just different directions. Situation here, I have a force of 10 newtons that was defined. I have a force that's undefined, and we want to find the magnitude of the torque produced by F. And I called that torque 1, which is negative because it's going to go clockwise. The 10 Newton torque, I'll call maybe torque 2. That's going to go counterclockwise, so it's positive. And so we know that the net torque is 0 because they told me that it was going to remain at rest. So I know that torque 2, which is positive, minus torque 1 has to equal 0. So they equal each other. Now I solve for torque 1, which is equal to torque 2, which is 6 Newton meters. Here's a situation. I have this meter stick. I know the mass of one mass of 2. Obviously, I should be able to determine R1 and R2. The axis of rotation is at this fulcrum. And then this is putting a force upward, which is going to be equal to Fg, which is mx times g. And we want to know the mass of x. Well, we know everything except for the mass of x. I can call this torque 1, torque 2, torque 3. All of them have to add up to 0. The only piece that I don't know is mass x. I know all the distances, so we have everything we need. This situation, I have a force downward. I know that that puts a 400 Newton meter torque. And they want to know, where does the student need to put a force? Well, I know for a fact the student needs to put a negative 400 newtons so that the rod remains in equilibrium. Okay, so if it's currently got 400 Newton meters, I'm going to put another 400 Newton meters, but in the opposite direction. So then I go through here and I calculate which one is 400 Newton meters. And only one, I'm sorry, two gave me the correct answer, and they told me to select 2 answers. Okay, situation, I have a student X, student Y. They are sitting on a seesaw, and they tell me that I know the mass of student Y. I don't know anything else, and I want to know how to find the mass of student X. Well, in order to set the torques equal to one another, I need to know the torques, and I also have to know the distances. So the thing that I need is the distances away from the center of the seesaw where the students are located. Last one. I have objects 1, 2, and 3 that are on a meter stick that's on a fulcrum that's located at the center. And they give me all the distances away, so I drew a diagram. And I labeled torque 1, torque 2, torque 3, determined which ones are positive. I also labeled their distances away. Those are in centimeters, so I'm going to use meters when I calculate this. And so then I actually calculated the torque that each one of those masses give me. Torque 1 gave me a positive 1.5, torque 2 gave me a negative 0.3, torque 3 gave me a negative 0.4. Notice the net torque of all that is added up to 0.8. If I want this thing to remain in static equilibrium, I need to add another mass somewhere such that it creates a negative 0.8. Okay, in order to create a negative 0.8, I have to be to the right of the fulcrum, because everything to the right causes it to rotate in a clockwise direction. Just because there's 2 on the right doesn't mean you have to have 2 on the left. It's related to the mass times the distance. So it needs to be to the right. That's, I know. So C and D can't be correct because it's going to be to the left. And now I just need to check A and B to see which one causes a torque of negative 0.8. And that would be B. And those are both negative because they are to the right of the fulcrum, creating a clockwise torque. And that's what we got.